better. So we will see that. Okay, and yeah, and now you can say that okay, I break this up into two subarrays. I sort both of them using a recursive procedure, and then you're going to combine them, right? So the question is, how does the combined step look? Right, so what is the goal of the conquer step? Which is, so now you have two sorted arrays. We have sorted B, which I will denote by this array, and sorted C. You have this. And how do you combine these to get a sorted A? Right, so the question is, how should this combination be done?
Just iterate across B and C.
Yeah, so how do you iterate across B and C?
Do it well, you know the first elements are the smallest in both arrays.
Okay.
And one has to be smaller than the other.
Right.
So just pick that one and put it back down in address A, the smaller one, and just keep doing it across both.
Exactly. So what he's saying is, you know, A is just the union of B and C, and B and C are both sorted, so these are in increasing order. Right. Now the smallest element of A has to be one of the leftmost elements of B and C, because both of them are increasing order. So you look at these two elements, okay, and pick the smaller of the two. That would be the first element of the sorted A. So let's look at, so this one is min of B of 0 and C of 0. So let's say that this was the minimum element. This was the smaller of the two. So now you can now think of it as just having two subarrays. Yeah, actually, now what would you do? So what would the next element of this one be?
Maximum of this set.
Sorry?
The maximum element of this set, B0 and C0.
Yeah, so that's the first mistake you can make, right? Which is that, so the second smallest element of this need not be the other one, right? Because your split could have been so that, let's say your numbers are like 3, 4, 7, 8 in B. So this is the sorted B, and C maybe is like 1, 2, 9, 11. Okay. So in this case, the smaller element is 1, right? So that's the first element. Now the second element is not 3, right? So the second smallest element is actually 2. So you should be now comparing whatever is out here with still the first element. Okay. So you have to be careful about that. Okay. And so that's what you do, right? So in other words, so the second element, so this one is now min of, still we have B of 0 and you have C of 1. Okay, so now you have and now again in this example it so happens that this one is the smaller one. So now what do you have to compare? What is the third element out here?
The minimum of B of 0 and C of 2.
Exactly. So it's a minimum of B of 0 and C of 2, right? So in some sense, this one, as long as this guy is not picked, you keep comparing this element with whoever comes in C. Okay. So the next element is these lines again. So it's min of So now finally B of 0 would get picked as the minimum one, and then from now on you start comparing with B of 1. Okay. So in some sense you always think of just having like a starting point, which is things until which you've covered. So usually people do it by having 2 pointers or something like this. So you have pointers that start off with both of them pointing to the leftmost element, and then you pick whatever is the smallest element, you write it to this sorted array, okay, and then you move that corresponding pointer to the right. Okay. So I will pause a little bit. Any questions about this algorithm? Yeah, because I've done I'm assuming that most of you, actually how many of you have not, firstly what is this procedure called? Okay, so this is merge sort, right? And how many of you have seen merge sort before? Okay, so yeah, this is what I anticipated, that's why I'm not going into too much detail. So are there people who have not raised their hands? Feel free to raise. Okay, yeah, so I mean I will have more details as notes, but yeah, but the basic idea, so do you understand the rough idea? Like if you have two sorted lists and you would like to merge them, right? So this one is in increasing order and this one is in increasing order. And if you want to merge them, then it's a very simple procedure. So in the merged list, you know that the smallest element has to be one of the smallest elements of those two. Okay. And now you just imagine removing the smallest element, and now you have two smaller lists that you now have to combine. Okay. So think of now this list, instead of being of size n by 2, it's only whatever this one. Okay. And now again, the smallest element in the union of those two is just the minimum of those two elements. That's what I wrote here. And then you keep doing. Okay. So the simple you're using is that B and C. For B union C. Okay, so I'm going to slightly misuse notation and say B union C. If there are elements repeated, I just mean you take them twice. Okay, so that's what I mean by this. Minimum element B union C is min of B of 0 C of 0. So now you can imagine deleting that minimum element from either B or C, wherever it came from, and then you recurse on the smaller thing. Okay, so that's essentially what is happening in this app. Okay, it's just that we are doing a clever implementation of this procedure. Okay. That okay, so that's essentially what is happening in this procedure. So now what is the overall time complexity of this procedure?
N. O N.
Okay, so
procedure?
of the overall procedure of like going first picking the smallest of this combined procedure.
The combined part. And
Why is that?
because you are iterating simultaneously across the two at length n. So
Okay.
you look at each element once.
So, but in this case, you are looking at this element multiple times.
Well, okay, yes, but you copy each element down once.
Okay. Right. So what he's saying is, I mean, in some sense, you copy each element down once, and at every step, you are at least copying one element down. Okay. So you are making some progress. Okay. So it's not like you're comparing the same elements each time. So you're always making progress. and each time you move exactly one element down. So that's the reason this procedure has to stop after n commit.
And even if you're comparing the same element over and over again, it's against a different element
Exactly.
in the other array.
So you are making progress in the other array. If you're not making progress in one array, you're making progress in the other. Okay, so that's the, but these basic things is just good to be extremely clear about. That's why I'm being very detailed. Okay. Yeah. So that's the point here. Okay. So we always make progress. So so let me come to the. Sorry. So the conquer step has running time. Okay, so this is what I just mentioned. So now let's just recap the overall procedure. So the overall procedure is simply, let me write down the procedure. So if you have sort of array A, n minus 1, right? So this procedure is basically the following. We said that create some arrays. V equals A. So I should be writing floor and so on here, so I will skip that for the purpose. And okay, so you create these subarrays and then recursively sort okay. So you sort B and sort C separately, and then run this merge procedure on sorted B. Okay, so the merge procedure is the procedure from this page. And that's it, right? So, and you just, this will end up, if you really want, you can copy back this merged thing into A. So, assuming that everything is copied back to A. All right, so this is the basic procedure. Okay, so now, how do you show the correctness of this overall procedure? Right, so let's see a bit more formally how you would do this. Okay. So I've already told you the template, right? So the template for analyzing most recursive procedures is you show that the base cases are correct, okay, and which tells me that I need to have a base case in the algorithm. Right? So here we didn't have a base case. So you just say the base case can basically be if n is 1, return the array. Okay, so that's the base case, and otherwise you do this thing, right? So that's what you do, and so the base case in this case is trivially correct. And now you say that by induction you assume that the recursive steps give the right answer, because this is what we do in induction, right? You assume that whatever you want to show holds up to a certain n, or up to some n. And then you prove the statement for n plus 1. Okay. So you assume that all these recursive steps give the right answer, and then you prove that the combination step is still maintains the right answer. Okay. So that's what you do in all inductive proofs. Okay. So any questions on this? Because this is very simple, but we will keep using this. So what this shows is that, I mean, what this tells us is that all you have to think about is this merge procedure. Okay. So in this case, so and this one we already have seen, right? So all you have to show is that this merge procedure, one where you pick the smallest element and keep going, gives us the right answer. And I've already written down the key step in the proof, right, which is this statement. That is, if you have two sorted lists B and C, then the minimum element of B union C is basically this. So this, I claim, is the key statement, and once you have this, the correctness of the whole merge procedure follows. So why is that? Do you guys all see this? Yeah.
Firstly, if the size of B and C was 1, then the solid combined iron would be whatever is the lower between B0 and C0 and then the next element. And similarly, we're just comparing one element with another. So the least element is the smaller element and
No, but so what I'm saying is you would like to show that the merge procedure that we've given, right? So the claim is if B and C are sorted and we run the merge procedure, the resulting array is the sorted version of A. Okay. So this is formally the statement that we would like to show, right? So if we want to show that the merge procedure is correct, this is what we mean. Okay. And you assume inductively that B and C were sorted correctly. Okay. So you have the sorted versions of B and C. Okay. And now you would like to show that if you ran the merge procedure that we discussed, you're going to find, you're going to end up with the sorted version of all of A. To show this, the first thing you must show is that whatever you output will actually be all the elements of A. Okay, so that's one thing you must show, and then you must show that they will all be in increasing order. Okay, is that clear? I mean, yeah.
So I think we should consider when the worst case happens and when the best case happens.
What do you mean by the worst case and the best case?
In terms of the purging and number of comparisons that we need to do.
So this is, so remember, we're not talking about the running time here, right? So there's no best and worst in terms of running time at this point. I'm only saying this procedure is correct, okay, and I would like to show that formally, right? Right, so it's not about what process takes more comparison, less comparison, so on. Okay, and all we are saying is this procedure, once it terminates, it produces the sorted version of the whole array. Okay, so it's in some sense a simpler statement than that. So yeah.
In our discussion, did we describe what happens or what we are supposed to do if B or C runs out of elements?
Yeah, not formally, but we should. Yeah, that's a good question. So what he's saying is, what happens if one of B or C runs out of elements? Okay. So in that case, I mean, if you ran out of elements, then you simply just pretend that whatever you ran out of is like infinity. Okay. So, but we should mention that. That's correct. Okay. So, yeah, maybe it's actually good to write down the formal Okay, so what is the merge procedure? Right, and what we are saying is this produces a new array. Okay. And you can either call it A, or if you like, you can call it something else. I'm going to call it A. Because we already have B and C. And what it does is every step until D and C are both empty. I'm going to write a procedure that is a little bit different from the way we implemented it, but you will see that both are the same. Okay, so I'm going to think of removing the first elements of B and C. Okay. So I'm going to have a procedure where I do that, and then yeah, you will see that both of these are the same. If B and C are both empty, you add minimum of A and forfeit remove it. From first marking. Okay. Yeah, and like you were saying, if one of the arrays becomes empty, if either B is empty, treat that B of 0 or C of 0, whatever corresponds to this thing, as infinite. So it never becomes the minimum value. Okay. So this is what you do. So I've written a slightly different procedure, but it's exactly the same as this procedure. Right? I'm just thinking of it as take the minimum element of these two, think of removing that element from C. So now C becomes a smaller list, and now you just have to merge all of B with B with that smaller C, and this is exactly the same procedure as that. Okay. Yeah.
So I think that's enough to prove the first part of the correctness.
Right. Yeah. So
because we want to show that, I guess that all of B and all of C are
show
merged
up
into
in A.
right?
Yeah.
Yeah. So
And you also automatically get that these have to be in increasing order by doing this procedure, because each time you add the smallest element of the current B union C. Okay, so I will come to that. But first, is this procedure clear? I mean, this is something that we often do when we are trying to analyze an algorithm. We just rephrase it slightly so that it's easier for the analysis, and then you can implement this by having these 2 pointers that we discussed earlier. Okay. So yeah.
By assuming that one of the arrays is infinity after it's finished, how does this gonna affect the comparison process?
Right. So when you treat this as infinity, then it means that min will always default to the other one. Oh, okay. So min of something comma infinity is that something, right? So min of x comma infinity is x always. Okay. So this is just this is just a notational thing. Yeah.
So could you say when B or C are empty, append the other? Would that also be
Yeah. So
one way of doing
implementing
that?
wise, that would be how you do it.
For the proof though, that's acceptable as well.
That's
right?
acceptable as well.
Okay.
Yeah. No. So all these are just different ways of saying the same thing.
Right.
So it's yeah. I would just like to say it so that it makes the proof as easy as possible. Yeah. Good. So this is the merge procedure for the sake of the proof. So now this is what we would like to show, and this would establish the correctness of the overall procedure. Right. So now we basically say that in the merge procedure we have, so again, so this is another observation. You could also call it like a lemma or something. Just that. So just for being very formal, we'll have two lemmas. The first lemma says that all the elements of B union C appear in. Okay. And lemma 2 will say that elements in A will all be inserted on. So both these statements will together give you what that claim. Yeah.
So these lemmas are with regard to our merge procedure?
With regard to the procedure. Yeah. So yeah, when you're analyzing an algorithm, you should state the procedure like I did here, and then you analyze it, and then you make some lemmas about this procedure, and you argue that each of these lemmas are. So yeah, I'm just trying to like be as formal as possible. All right. So the first and note that these two immediately imply the claim, because it says that all elements of A appear, or B union C appear, and it will also say that they will be in increasing order. So right. So firstly, why do all the elements of B union C appear? Yeah.
By like doing an induction to show that the lists become one smaller every time. Eventually it should reach like n or something.
Right. I mean, so you can do this by induction. Ultimately, you can just observe that you're running this procedure until B and C are both empty. And then each time you're adding precisely one element from B, one element of C to A, and you're removing that element from the corresponding array. So it's never going to appear again. Okay? So which means that if an element has been copied to A, never appears again, so it appears exactly once. Okay? And you're running this procedure until both the lists become empty. So everybody is going to appear at least once. Okay, so let me write down the two steps because I see some people not convinced. Okay, so let's write proof of limit 1. Lemma 1 is basically by observing that once an element of A or B, of B or C, it gets deleted. So it never shows up again. Second, the procedure runs. Until B and C become empty. Rest all elements in B and C show up at least once. And that's the procedure. And that's the proof, right? So it shows that nobody appears more than once, and now you're showing that everybody appears at least once. Therefore, from these two, whatever you want for. Alright, yeah. So that shows lemma 1. And the next lemma says that elements that are written to A will be in increasing order. And why is this true?
Because every time we pick the minimum element.
Right. So each time you always add. You know that B and C were sorted to start with, and each time you pick the smallest element. So this is also obvious in this case. So proof of this is because in each step we pick the smallest element of the current B and C. So B and C keep reducing in size, and each time we pick the smallest element of the current B. Okay, and this is why it will always be increasing. So whatever comes later will have to be only large. Okay, so yeah, so this is a formal proof of the correctness of this procedure, and yeah, once again we will find more details in classes. Okay. So maybe I will pause for a minute. If you have questions, you can. And then we'll look at the runtime. Yeah.
So just at like a high level,
Uh-huh.
these proofs, we want to like first establish a claim,
Right.
and show the procedure, and then make observations about the procedure, and then prove the observations.
Sometimes the observations would just be immediate. Sometimes they may require proof. Like in this case, right? So this is something that I wanted to also. I mean, if you guys are not used to writing proofs, I would always advise you to follow exactly what he's saying. Here it is: start with a claim, okay, which you would like to show. This claim shows the correctness of the algorithm, right? And that should be logically clear. And then you create a few lemmas or observations, whatever you like to call it, that would together imply the claim. And then you try to prove those separately. Okay. And coming up with a structure often takes a little bit of intuition. It takes a bit of time and so on. But that's often the cleanest way to write a proof. And this is what you will see in most of research work. And so you would like to come up with clean statements that would imply the claim that you would want. And each statement you would like to prove it, right? So and you would like to show it formally. And yeah, writing it down as like separate points is always nice, because each statement you should be able to easily check, or it should follow from something that you shown earlier. So yeah, so if you feel confused, just think in this clean way. Yeah.
Okay, so as far as doing proof on like homework goes,
Yeah.
It's like the degree of formality and depth. If we were asked to prove, merge sort, if we had just written down sort of what we can have here in tomorrow, would that be sufficient?
Right. So if you had written, yeah. So what would I expect you to write? Yeah, that's a great question. Right. So from point of view of like writing proofs in homeworks, how should you write down, let's say, the proof of correctness for merge? Right. So what you would like to say is, first we will do a proof by induction. So for that we have to do a base case. You have to assume that the recursive steps give the right answer, and you only have to show that this combining step is correct. You say the base case is easy, and this you can assume by induction. And then you get to this part. You write down that claim. So proving that the combination is correct basically means that we have to show that claim. And then you say that these are the two lemmas from which that claim obviously follows. And then you say that from the way we've defined the procedure, lemma 2 is very easy to see because you always pick the smallest element. And lemma 1 can be proved using these two steps. Okay, so that would be the overall proof. Yeah, actually, if it helps, I will write it in this format in the lecture notes so that you guys can just read it. Okay. Yeah. So, yeah. All right. So that's how you. Yeah, well, that's a good question. And I always like it if you just write it as points because it becomes easier to verify. Yeah, as steps. Yeah.
I think the thing that might be tripping people out is that in street math for proving claims, they would say prove that this sum is bounded by this or whatever, whereas it's proving a process here.
Right.
So once again, it's like creating the observation and potentially proving each one of those little observations are done by induction.
Right.
I guess I'm just confused on your first the slide you were just on.
The previous one?
Yeah.
Okay.
Like, why do you have to prove the third one but not the second? Like, why do you have to prove the combination is correct but not the recursive step? I understand.
Oh, that's a good question. Yeah. So you're asking, I've shown this. Why didn't I spend any time on this? Right?
Yeah, and I know the induction, like, you make some sort of assumption and then you like prove the the following step or whatever, but it doesn't feel like that here. It feels like those are very two distinct steps that
right. So, but the point is that so what is how does a proof by induction go? Right. So it says that you assume the correctness for all instances of size strictly less than n. Okay. Assume that this procedure, that the overall procedure you have, which is the sort procedure. So let me be a bit more formal than that. So proof by induction would basically say the following. Right? It would say that sort of A returns the right answer when n is 1. So this is the base case. Then it will say, suppose sort of A returns right answer for all sizes less than some n, then for size n, right? So proof by induction, you have to show these two steps. Okay. If you have shown these two steps, then it means that this procedure holds for all n. Okay. So if you want to be really informal, for n bigger than 2, assume n. So for all n bigger than or equal to 2, you have this statement that suppose sort of A returns the right answer for sizes less than n, then it also returns the right answer for n. Okay, so that's so this is a proof by induction, right? You always you would like to show two things. The first is the base case. Next is the inductive step. Base case in this problem is this. The inductive step is You assume it returns the right answer for all sizes less than n, show it for n. Okay? Yeah.
And so the work where we proved the two lemmas was proving the assumption.
Was proving the second case. No, so this assumption is not, this is not an assumption. Yeah, so this is like say for any n bigger. Yeah, it should be like let n be anything bigger than or equal to 2, then you would like to show this thing, right? So this is the base case, this is the inductive step.
Where's the assumption?
What do you mean?
That's what I know about induction, which you like make an assumption and prove it false. Is that what it is?
Right. So the suppose is like an assumption. Yeah. So you assume that sort of a returns the right answer for sizes less than n, and you show it for n.
And then prove for n.
Yeah. Okay. So all proofs by induction follow this thing. Okay. So if you, I mean, if you guys haven't seen it in the recent past, you should go back and look at some proofs by induction, and they always follow this procedure. First, you prove the base case, and in the case of analyzing an algorithm, you say that you basically define a few base cases. In this case, the base case is just n equals 1. Prove that whatever procedure you define works for that. And then you say that suppose it works for all problem sizes strictly less than n. You will prove that it works for problem size equal to n. Yeah.
Okay, so that makes sense. I like that. But how does that translate to that previous slide where you were proving, or you were assuming the recursive step, proving the combination step? It just feels like two distinct things.
Right. So now what are all the recursive steps doing? Right. So if I give you an array of size n, you are creating subarrays and you're running the same procedure on the subarrays. The subarrays have a size that is strictly less than n. Correct? For any n bigger than or equal to 2, the way I have defined these subarrays, they have size that is strictly less than n. Okay? And then so this thing where I'm saying that suppose sort of a returns the right answer for size less than n would imply that these procedures gave the right answer. Make sense? Okay? So that's the reason you don't have to prove, but you have to make sure that these sizes are actually strictly smaller. So you can't accidentally create something that's the same size. Okay? So alright. So that's yeah, these are all great questions, and also some of these things you have to like go back and think about them a bit more. Okay, so you should do that. But yeah, so this is what all proofs by induction look like. So you first want to show the base case, you want to show these things. And one thing you should remember is that the problem size need not always be what you do induction on. Okay, so we might see some examples of that later. Okay, so that could be something else. Good. So yeah, so let's move on to the next thing, which is the running time, right? So how do you now analyze the running time, right? So as I was saying, there's only one way to analyze the running time, which is go through the algorithm, go step by step, and try to analyze the running time of each line. So this one is just a basic check. So this takes just some constant time. How much time does this procedure, does this step take?
It kind of depends on whether or not you're just simply partitioning the existing array or if you're actually copying the existing array into new.
Right, let's say I'm copying the existing array. So this takes n time.
N
right?
time, yeah.
Yeah, you can be conservative and say n because you will realize the merge anyway takes n, so might as well be conservative.
So it's linear.
Okay, so but you're right. I mean, if you don't want to copy, you can just treat it as a constant time operation. But yeah, it's not good there. And now sorting. So these are recursive steps. So we don't know for now, let's keep these as they are. So these are some recursive function calls that we need to analyze. And then you have the merge procedure. And we just saw that the merge procedure takes time O of n. So this, haven't like formally shown it, but we mentioned when we were discussing it that the running time of this merge procedure is n. Okay. So, alright, so that's, so this is what we have. And now these are recursive function calls, but we know that they are function calls to arrays of size n by 2. Okay. So when we want to talk about the running time of an overall procedure, so the common way to do it is to say that let E of n be actually let me be a bit more detailed to start with. So time of so let me summarize what we discussed. So time on the array A equals 1 plus n plus time on the array B plus time on array C plus again n. I'm ignoring consequence. O of n I'm treating as n. Okay, so this is what that step-by-step analysis said. Okay. And this is an array of size n. And these two are arrays of size n by 2. Yeah.
So where is the time spent in the first case? Is that to copy?
That's to break the, yeah, exactly. Copy this into two different arrays B and C. Okay, so this is just, yeah, this is just something that we observed from the previous slide. Okay, and now, yeah, so to make this more formal, so you can say that, okay, let E of n be this is the time taken for sort procedure on an array of length n. Then what the previous statement is telling us is that T of n equals 2n plus 1 plus 2 times T of n by 2. Okay, and I'm going to be conservative. So this again is like O of n. So I'm just going to replace it by. It's going to be a bit informal, and I'm just going to write this as T of n equals 2T of n by 2 plus some. So this is what we have. Yeah.
So where is that plus 1 comes from?
Yeah, the one is just the checking for the base case. Yeah, I mean I just counted it as an operation.
Shouldn't we consider the worst case of number of comparisons that we need to do that constantly? And in this case, it should be 2n minus 1. No?
What do you mean 2n?
The worst case scenario happens when the all elements of the B except the last one is less than the array C, and the last one is largest than all the elements of array C.
Yeah, so actually there's a good exercise for you guys to think about. So what he's saying is that in this process, depending on how these elements of B and C are arranged, sometimes you could take more number of steps than the others.
Yes.
If you think about it a little bit, you'll realize that's not true. You'll always make exactly the same number of comparisons, because to write down one output, you're doing one comparison. Okay, doesn't matter how these are ordered.
But what happens is that if the list is empty, right?
You could avoid making comparisons, but the way I've defined the procedure, you're still making a comparison with infinity. Okay. So yeah, but these are all minor things, right? I mean, these are like n by 2 versus n. So one thing you should realize is that constants of small magnitude don't really matter to us. Okay, like if it's a 2 factor here and there, we don't care that much for optimizing. Yeah.
So if we're writing a proof on an assignment, can we just drop small constants like that?
Yes, you can just use big O notation, right? You can just say that this takes O of n, that takes O of 1, whatever, and you can drop constants like that. Yeah, for the purposes of this class, you can drop constants of whatever size you want. So, in practice, sometimes it hurts, but yeah. Okay, so in general, this is what we have, right? So T of n satisfies this condition that it's 2T of n by 2 plus O of n. So this is nice, but it's not a closed form, right? So it's not saying T of n is some, n or n squared or something like this. Okay? So equations of this kind are what are called recurrence equations, recurrence relations. And so the general form is you have some function of n. In this case, that is like T of n. And you will have it as some explicit function of the parameter n, f of 1, f of 2 up to f of n minus 1. Okay. So you will define the function value at n as a function of the function values at integers less than n. Okay. And this is the most general form of a recurrence equation. Okay. So in this case, we have this thing of T of n equals 2T of n by 2 plus O of n. Right? So let me write that O of n as something like C times n. Okay, just for concretion. C is some constant, 2 or 3 or whatever. Okay. So that's the form that we have. But in general, you could have something more complicated. Like you could have something like T of n equals T of n minus 1 plus T of n by 2 or something like that. In your homework, you will see multiple examples of this. Something of this kind. Okay? And so often, finding a closed form for this is what you're interested in, right? Because while this is perfectly fine, it doesn't give you too much about what the function T of n is. Right? It just tells you it's 2T of n by 2 plus n. Right? But what is it actually, right? As a closed form, as a function of n. So finding these things can sometimes be challenging. Okay? But often it's not too challenging. Right? If you work on it for a little while, you'll be able to get a hang of it. Right? So now, how do you? So in analyzing algorithms, one of the things is to be able to come up with closed form solutions, because we are not very satisfied with an answer like that. So how do you come up with closed forms? Again, I'll start off by saying there's no silver bullet, unfortunately, right? So you have to try a few things, but there are many techniques. Okay. So how many of you have seen, let's say, the master theorem? Okay, so about 50%. Okay, and yeah, so there are many techniques to solve these kind of recurrence equations. And as I was saying, there's no one technique fits all. And we'll see a couple of them in the course. Okay, so there is this. For this simple recurrence, I will do a couple of techniques today. Okay, I will do this I'll do these three. And yeah, so the master theorem and Akrabazi theorem, these are things which, yeah, I personally think that they are too specific. But people like to study them, so I'll have some lecture notes linked that will have things to this as well. And yeah, as I was saying, my personal favorites are always have been this. Recurrence tree is nice if you, for basic examples, but it starts breaking down very easily, and also trees become messy once they're not uniform. Okay. So these other things are easy. Okay, so let me give you examples of this by actually doing it for this simple case. Okay, so let me show what this means. So suppose I want to solve this recurrence. So you have T of n equals 2T of n by 2 plus C times n. C is some constant. If you really like, think of C as 1. Okay, I mean, if you don't want to think of this parameter. So what does a proof by a recurrence tree look like? So what it says is, so let's try to unpack what T of n is. Okay. So this formula is telling us that there are two steps of T of n by 2. Okay, so T of n is this plus C times n. Okay. So that's what this formula is telling us. And also there's always a base case. So in this case, T of 1 equals 1. Because you have to have some kind of a base case. Okay, and you have something like this. And now you can use this formula inductively to say that T of n by 2 will be T of n by 4 plus T of n by 4 plus C times n by 2. Correct? Because I've used the exact same formula with n replaced by n by 2. Okay, so that gives us n by 2 divided by 2 is n by 4. And same. So is this clear? Steps so far. Okay. And you have the same thing out here. Okay. And Cn is just Cn. So there's nothing that and now you can imagine further dividing this and so on. Okay. So now we can see what's going on, right? So at this step, you have 1 T of n. Okay. At this step, you've got 2 such T terms, and each of those is like T of n by 2. At this step, you've got 4 terms that are all T of n by 4. At the next step, you'll have, what will you have?
N by 8.
Yeah, so you'll have 8 terms that are all T of n by 8. Okay, next step, and in general, after some r steps, you'll have 2 to the r terms that are all T of n divided by 2 to the r. Okay, at depth r of the tree. Okay. So these are the T terms, right? What about these constant terms? Because these are actually the amount of, these are some work that you are doing, right? Right? So what is the total amount of work you're doing of this, like additional work you're doing at this level? So here it's just C times n, there's only one term. Okay, like these extra terms, there's only one term, so it adds up to C times n. What do all the extra terms here add up to? C times n. So here again it's C times n because there are 2 terms that are C n by 2. So this adds up to C of n. Total C times. So if you think about it here, you will have 4 terms that are C n by 4. Okay, so the total turns out to be again C times n. Okay, in the next step. And so that keeps going on. So the nice thing about this tree is that these extra terms at every level add up to C times n. Okay. So that's good, right? And so now you can ask, what is the overall learning time procedure, right? So firstly, how much do you need to expand this tree? I mean, yeah, so you have to do this until you get to the base case. So the base case is the only case where we actually know the value of t. So you have to get to the case where you know what thing is. So you need n by 2 to the r to be 1, which means r should be log n. Okay. So you expand this tree. So r equals log n. Now in this case, what happens? So you have, right, so you now have a tree of depth equals log n. Now what is t of n? So now how do you now compute what is the value of t of n? Remember that I'm just viewing that computation as being done over a tree. And the Cn I have to pay for computing the value of t of n, right? So in order to find out what this value of t of n is, I must add up two kinds of terms. One is these extra terms that show up in each level, okay, and these t of 1 terms that show up at the root, at the base of the tree, at the leaves. Okay. So you can think of t of n as sum of all the C of n type terms. All the levels. Okay. Plus t of 1 terms in the last level. So this tree procedure is somewhat, it's heuristic, right? So that's why it's being so informed. Okay, but yeah, so this is what you've got to add up. Okay. Now I've already told you that in each level, these C times n type terms add up to exactly Cn. That's what we observe, right? The first level is Cn, next level you have two terms and a Cn by 2, so on. So this part would add up to Cn times log n. Okay, because R is log n. That's the number of levels. And how many t of 1 terms are there in the last level? You had 2 to the r, and r was log n, so you had exactly n terms. So these are 2 to the r times t of 1, and this one is n times t of 1. So this what gives you the overall running time, t of n is Cn log n plus n, which is of course O. So this is like a very detailed way of doing the running time for this simple example. Okay, and as you will see, this tree method, some people like it, but it's often somewhat cumbersome. So some of the other things we'll see next class, which will be out of time, will be make this a little bit easier. Yeah.
Why is it C and log?
Oh, yeah. So I mentioned that these extra terms, right? So T of n is T of n by 2 plus T of n by 2 plus Cn. Likewise, each of these T, when you're computing T of n by 2, you'll have this extra term, right? And in this level, there are two extra terms each being Cn by 2. So their sum is C times n. Okay? And in the next level, you'll have 4 terms that are all Cn by 4. Okay? And that adds up to a total of C times n. And you have those showing up at every level. And we know that there are R levels where R is log n. Okay? So each level there's a total work of like C times n that you're doing. And there are R levels. So there is R times Cn. Okay? And R is log n, so that's why it's Cn log. Does that make sense? Yeah, you can stop by here.